Hey, 3, 2, 1. All right, welcome to the first of a pair of videos here for our third week. As per the announcement, we have welcomed our second child. So, yay! So this week we'll do some online lectures. We'll get back to normal next week. Although at the time of the recording of this, Olivia has not been born yet. But yeah. Anyway, so it's just we've scheduled the induction date. So I'm getting this filmed as if there's a camera, recorded right now. Okay. All right. So this is the first of a pair of videos to finish up chapter 1, and when I see you in person, we'll jump into chapter 2 for a little bit, then over to chapter 4 and do some vector space stuff. Then we'll bounce back to chapter 2, then we'll go to 3, then we'll go to 6. Makes complete sense. But alright, so let's talk fundamental operations with matrices. So we've already introduced the idea of a matrix, but let's sort of remind ourselves of what's going on. So a matrix is a rectangular array of real numbers with m rows and n columns, written as follows. And the entries, we denote the rows in the first spot. So here's the first row, down here's the mth row, and the second indicates the column that it is in. So we do rows, columns when we denote them. Now it's worth stressing, like I said, that formally speaking, if you want to actually create the matrices from scratch, they're functions whose domain is ordered pairs of positive integers bounded by m and n. So that means when we're going to deal with matrices, we will denote them as capital A, and we will work with them and talk about them directly with their entries. So the jkth entry will be denoted like this, and again, think of it as an output of a function whose inputs are two positive integers. All right. The collection of all m by n matrices will be denoted with a fancy m sub mn. So the set of all matrices with m rows and n columns. So this is the notation we will use. As I mentioned, there's other notations out there for the set of matrices, but this one does the job. All right. So again, it's worth stressing the set is non-empty, and in particular, always has the zero matrix, which is the matrix whose entries are all defined to be zero. So again, you can create matrices just like you can create elements of Rn by explicitly telling me what the entries are. Right, so in this case, all the entries are zero. Not too much there. It's worth noting if we have to include some notation to indicate the 3 by 2 zero matrix, we can do that if we want, but normally from context you'll understand which zero matrix I am referring to. Beautiful. All right, so something we didn't mention in person, so there is a special class of matrices that's worth discussing, the n by n matrices, or the square matrices. So as we will see as we go forward, the matrices that have the same number of rows and columns are going to play a very special role in a lot of the theory of linear algebra and the theory of solving systems of linear equations. Now that should hopefully make a little bit of sense, because if we think about a system of linear equations where the matrix ingredient is square, that means the number of rows is the same thing as the number of columns. So in other words, the number of equations we have is the same as the number of unknowns. 2 equations, 2 unknowns, should be able to solve that. So hopefully it's not too surprising, and of course we're going to get to all of that. All right, but in the meantime, it's worth noting that within the square matrices is a very important matrix, a matrix we will frequently use and frequently reference. So let's take the moment to introduce it. It is the identity matrix. So it is the matrix defined as follows. It has the property that the jkth entry is 1 if the j and the k are equal. So if you are in the same row and same column, it spits out 1, and if they are unequal, you get 0. So a couple of examples gives you an idea of what this matrix looks like. So the 2 by 2 identity matrix, note I sub 2 in the notation indicating the sizing of the matrix, right? 1 in the 1, 1 entry, 1 in the 1, 2 entry, 0 in the 1, 2 entry, and 0 in the 2, 1 entry. And likewise for I3. Note, 1's on the diagonal, 0's everywhere else. Nice way of thinking of it. So formally it's this, but informally, 1's on the diagonal, 0's everywhere else. And it's worth stressing that when the size of the identity matrix is known from the context, we won't include the sub n. There are a couple of spots where it's good to remind ourselves of the size of the particular identity matrix you're working with, as we will see. But for now, we'll just go with that. All right, cool. All right, so as we also discussed previously in class, matrices, much like elements of Rn, can be scaled and added. So given a matrix, you can scale it, and the formula is what you think. Right, the JKF entry is the scaled JKF entry of the matrix. Likewise, if you want to add two matrices together, the JKF entry is the sum of the JKF entries. And similar to Rn, there are 8 properties this all satisfies. And again, I'm not going to prove any of these 8 because all the proofs are exactly the same as they were in Rn, only now instead of 1 index, there are 2 indices running around. But again, it's worth reminding ourselves what these 8 specific properties say. The first 4 are telling us that the addition of matrices is very well defined. It does the properties we want, the commutativity, the associativity, the identity, the existence of inverses. So for the deep lore enthusiasts, it's an abelian group. And the scaling and the adding all interact in a way that you'd want them to. Much like Rn does. So maybe when we get the vector spaces, these are the 8 properties that they need to have. Maybe. We'll see. Anyway. Alright, so like I said, we're not going to prove these 8 facts are true, even in the other type notes that are available. I didn't include the proofs, but if you want to go about proving them, feel free to do so. But let's prove something so we get a bit of a taste, a bit of a feel for how this stuff works. Alright, so let's specifically prove something that we saw before. So let's say you've got a scalar R and a matrix A, and we know that the scaled matrix is equal to the 0 matrix. Okay. Then either the scalar is 0 or the matrix is 0. So let's prove this. Okay. So again, it's an OR statement, so we can prove it by starting with, hey, suppose this doesn't happen. Right? Because again, an OR statement is true if both components, or if at least one component is true. So if I knew C was equal to 0, well, then the OR statement is automatically true. I don't care if A is 0 or non-zero. I know the first thing is 0. I need at least one thing to be true. So instead of even worrying about that case, we just need to establish what happens when C is non-zero. Specifically, when C is assumed to be non-zero, then A must equal 0. Alright, well, let's suppose that C is non-zero. Our hypothesis here is that the scaled matrix is equal to 0, which means that the JKF entry of A times C is equal to 0. But C itself is non-zero, so it's got to be that the JKF entry of the matrix is 0. That's good for all J and K, so A and the 0 matrix are identical. They have the exact same entries, so they are the same matrix. Good stuff right there. Beautiful. Beautiful. Okay, cool. So I give this a little flavor of a proof, and note that, again, not exactly that different than what we kind of saw for Rn. Right, just a simple sort of, getting in there, working with the nitty-gritty with the indexing. Not too bad. Not too bad. Okay. Alright. Well, let's up the ante a little bit and start introducing things that are matrix specific. So far we've kind of been repeating here that, hey, this is just kind of shit you can do in Rn, only now there's 2 indices. Alright, well, let's actually make use of the fact that we have 2 indices, explicit use of the existence of 2 indices. So given a matrix A, its transpose is the matrix defined by swapping the rows and the columns. So formally that's written out like this, but note the sizing in M by N matrix becomes an N by M matrix. Good stuff, and we actually worked out the details of the proof of the first fact here in class. Right, so if you transpose a transpose, you get yourself back to normal. And transposing a scaled matrix is the scaled transpose, and transposing a sum gives you the sum of the transpose. So, in other words, transposing is a very nice operation for matrices. And it's going to be shocking as we go forward in this class how incredibly powerful transposing is. Just this idea of swap the rows and the columns, that seems like just like an arbitrary maneuver that we can perform, right? That seems like, yeah, you've got a rectangular thing, so you have rows and you have columns, change the rows and the columns. It doesn't seem like that should do anything particularly impressive. It just seems like that's something we can do. But time and time again, we are going to see as we go through this course, that maneuver, like, you can get away with so much stuff with it. And here we kind of get a brief little sampling of transposing undoes itself, so that's kind of like, oh, that's interesting, which not the most exciting thing. Formally, so if you're interested in a operation that undoes itself, those are called involutions, and look up involution algebras if you want some real stuff there. Involutions play a very big role in a lot of branches of mathematics, so cool stuff. But also, facts 2 and 3, as we noted, reveal that the operations that we have access to in the matrices, scaling and adding, transposing respects those operations. So it respects the scaling in the sense that transposing something scaled just gives you the scaled transpose. Same thing with addition. Transposing a sum gives you the sum of the transposes. Or transposize. Transopites, maybe that's the correct. It's like the proper plural of octopus. Is it octopuses or octopi? And the answer is neither. The correct plural is octopodes, because that would be the Greek pluralization of it. Whereas octopus is a Greek word, that's how you would pluralize it. Octopodes. So, the transtopodes. There you go. Anyway, alright, so as we noted, we did proof 1 in class. And the main thing that we want to kind of stress when you do these indice proofs is be careful of where these live and make sure, like, sizing is lining up right. So, for example, in point 1 here on the proof, J and K live between, J lives between M and K lives between N, right, because the matrix A is an M by N. However, here in point 2, J is between 1 and N, and K is between 1 and M. That's because this matrix, CA transpose, is an N by M. So when we do these proofs that are relying on the entries of your matrix, it is worthwhile to remember where they need to live, and especially when you've got rectangular matrices, so you've got to be keeping track of the dimensions and what letters we're using for those, and especially when transposes are flying around, because we will be swapping. So similar for point 3. But again, the actual proof content, like this part right here, like, big exercise in parentheses and index management, right? It's not like deeply enlightening. It's very mechanical. It's very just we need to do this because we're going to use these facts. In fact, we're going to use them right now to prove some cool stuff. All right. So specifically, let's introduce the next ideas. So a matrix is said to be symmetric if it's equal to its transpose. And similarly, it's called skew-symmetric if it's equal to its negative transpose. All right, so first of all, note, a matrix needs to be square in order for you to even talk about this. If you're symmetric, then A, you're equally transpose, and hey, I don't have the correct... Oh, I don't have the correct symbol there. I got that gross T. I don't have my top. I didn't read it. Are they all T's? They're all T's. Boo. Boo! Oh no. Well, gone too far now, so. Oh well, we gotta deal with this ugly T. Look at this thing. Look how beautiful. Look how majestic that is. Look at this pedestrian trash right here. Absolute pleb. Let me tell you. Anyway. Alright. But anyway, so a matrix is said to be symmetric if it's equal to its transpose. And now, what does that mean? Well, that means the rows are equal to the columns. So, for example, the identity matrix is nice and symmetric. And skew symmetric is a little bit different. It's a little weird, and at first glance it might be, why even consider this? This seems like the more interesting thing. And in fact, as we go forward, you're going to see symmetric matrices are very nice. They got some neat properties. But skew symmetric kind of comes along for the ride, and you'll see in your homework how symmetric and skew symmetric actually interact with each other to get a pretty nice little theorem. So later on in the course, when we start talking eigenvalues and eigenvectors, it turns out that the symmetric matrices, there's some stuff we can say about their eigenvalues. And the skew symmetric ones, there's actually something really neat you can say about their eigenvalues. So they'll play a much bigger role later on. For right now, let's just work with these, because this is going to demonstrate to us why we needed to do this proof first. Right, so note we did this proof to prove that transposing works well with scaling and adding. And here we worked out the gross index details. But now, equipped with those, if I want to prove that A plus A transpose is actually symmetric, it can be easily demonstrated, because I know the transpose of a sum is the sum of the transposes. I know the transpose of a transpose is the original matrix. And I know matrix addition is commutative, so I can swap it. And there we go. That's what you needed to demonstrate to verify that A plus A transpose is, in fact, a symmetric matrix. Cool. Right? So note, it behooved us to take the time to work out these sort of boring and or gross or, not exactly the most exciting proof, but equipped with it, proving that A plus A transpose is symmetric now has a nice little one line, 3 equal signs, beautiful proof purely built off of algebraic properties, purely built off of things that we know, right? So we love proofs like this, and we want our proofs to be like this. That comes with a price, that sometimes we have to work out details of a proof that's it's not the best, but it pays off. Right, and that's going to be, again, we kind of saw that when we built up to like the proof of the Cauchy-Schwarz inequality, where we got to do all these like little things and put the machinery together, and then it comes together in a huge way in a really cool proof, a very important fact. And right, that's going to be very thematic for this course. A lot of our proofs are going to be kind of trudge through some index stuff, build up to these nice tools that we then have, and put them together for a nice big picture. Cool. Very long-winded way of saying, this is the cool proof, right, dudes? Am I right? My dudes and dudettes. All right. And similarly for A minus A transpose being skew symmetric, right here we see that, yes, the matrix is equal to its negative transpose. And similarly, a scaled symmetric matrix will remain symmetric because the scalar will just go along for the ride. Likewise, for a skew symmetric matrix, transposing it, scalar just goes along for the ride. So we're happy about that. And these 4 facts will come together in a fun homework problem that you will see. I was pausing there because I was trying to think of something more eloquent, but yeah, words, whatever. Okay. All right, well, let's wrap things up now with another matrix-specific maneuver, and it's going to, again, be one of these sort of, yeah, this is the thing you can do, and it's going to be very surprising how useful this ends up being. There's a lot of things like this with matrices, and where it's just like, that's certainly a thing that can be performed, but it's shocking how useful it is. And this is the idea of the trace of a matrix, which is just add up the diagonals. Go down the diagonal of the matrix and add them all up. That's all it is. And very quickly we can get some basic facts of this for free. Specifically, the trace of a scaled matrix is the scaled trace. The trace of a sum is the sum of the traces. So, ooh, hey, just like transposing, this respects the scaling and it respects the addition. Hey, that's two completely different functions now that we've seen that do this. Oh boy, I wonder if that's like an important thing we should pay attention to. Alright, and as a last little bonus, the trace of the identity matrix is equal to n, and that's hopeful. That better not be shocking. Right, add up the diagonal entries. There's n ones. Alright, so, yeah. Proofs here are not the most challenging, worth doing, right? Again, to get us used to working with sigma notation, because oh boy, we'll be working with sigma notation. So gotta get on that great sigma grind set. Let me tell you. All right. So yeah, the trace of a scaled matrix. Well, right, the scalar's there. You can pull it out. Same deal with the summations. You can pull them apart the way you want them to, and adding up 1 n times just gives you n. That should not be shocking. All right, cool. And with that, that completes all of the fun and exciting details about chapter 1. Section 1.4 out of our book here. So now we've seen not only the fundamental operations involving the scaling and the addition of matrices, we've now introduced 2 maneuvers that are a bit more matrix specific. So scaling and adding is something we did with elements of Rn, but now we've got transposing and taking the trace, which really use the fact that we have double indexed things. And as we will see, these at first glance might seem like, yeah, sure, you can do this. But as we go forward, you're going to see, oh, good thing we can do these, because you can get some cool things proven there. All right. Okay, so that is it for the first video. Hope you've enjoyed it. And I will, you'll hear my dulcet voice for another video, and then we'll see each other in person again soon. All right. Hope you liked it.